Hello, welcome back. This is still Ken and we're on lesson 7 of our course on mechanics. And lesson 7 is about the potential energy and energy conservation. So these are our goals for this lesson. First, we are going to use the concept of gravitational potential energy in problems that involve vertical motion. Second, we are going to use the concept of elastic potential energy in problems that involve a moving body attached to a stretched or compressed spring. And our last goal is to learn the distinction between conservative and non-conservative forces and how to solve problems in which both kinds of forces act on a moving body. First on the list, we are going to study the gravitational potential energy. The gravitational potential energy, or simply the potential energy, is the energy associated with your position. And like say for example, here you have your metal ball, which will be later used to destroy a building, or you call this one as your wrecking ball, if you know Miley Cyrus. So this wrecking ball here is at some height, h, okay, with respect to your horizontal, which is set to your y equals 0. So you have some position, and of course, this wrecking ball here is affected by the force due to gravity. This force due to gravity is then connected to what we have here, which is your gravitational potential energy. It's called potential energy because from the word potential, meaning it has a potential to do work. So it's again, it's from the word potential. It has the potential to do work. So like for example, later, if this wrecking ball is dropped, this wrecking ball has a potential to do work, like say for example, on something which is on the ground, or yeah, something on the ground. Or if you can imagine, you have a stone in at the top of your head, a stone at the top of your head. Okay, so the stone is at some height h, and if you're going to what do you call this? If you're going to drop this stone, of course, this stone has a potential to do work on your head. So you feel that energy as something that hurts you. So it's the potential energy of the ball that, or of the stone that hurts you. The gravitational potential energy is mathematically described as your u grav, that is equal to mgy. So you might ask why here we use your symbol U for your gravitational potential energy. Why not P? In later parts of our classes, we're going to use the letter P a lot. So in order for us not to be confused with what we're referring to, we're just going to use the letter U for your potential energy. So you have U grav for gravitational potential energy, and it's equal to your mass times your gravity times your height y. So again here, your U is your gravitational potential energy. So your potential energy. And your M is for your mass. Your G is, of course, your acceleration due to gravity. And then your Y is your height or your position. The figure on the right shows how the change in gravitational potential energy is related to the work done by gravity. So for this case here, you have a box that is at some initial position, and let's label the initial position as your point 1. And at point 1, your box is at height y1. And at later time, your box moves downwards at point 2, at this point here, and at some height y2. So again here, your box moves downwards, so you have here a displacement that is downwards. Now let us find the relationship of your work done by gravity and then your gravitational potential energy. So again, the work done due to gravity, or your work, is just equal to your force times your displacement s. And here your force is the force due to gravity, which is your weight, W. And your S is equal to your Y1 minus Y2. Your weight is just equal to your mass times your gravity. And your work due to gravity is equal to mg, Y1 minus Y2. And since your Y1 minus Y2, this is just equal to the negative of your Y2 minus your Y1. This term here in the parentheses is just your change in your Y, and you have here a negative. So here you have your work done is equal to the negative delta U gravity. As you can see here, you have this negative sign, which is very important because it gives you the correct work done for your system. Like say, for example, here, your box has a displacement that is downwards. So again, it moves downwards. And here, your force is also downwards. So your force and then your displacement is in the same direction. So thus, your work should be positive. If you're going to look at this equation, okay, so that equation, your work gravity, let me erase this one first. Okay, so your work due to gravity is equal to the negative of your mg y2 minus your mg y1. Okay, so if you're going to use here, as you can see here, your y2 here, this is less than your y1. So y2 is less than y1. So if this negative sign here is not present, it will give you a negative work done, which is false because here your force and then your displacement both are in the same direction. So your work should be positive. Here, if your box is at some point 1 and then it goes to this point here 2, you have here your height y1 and then here your height y2. Here your y2 is greater than your y1, but for this case here, the force due to gravity is still downwards and your displacement is upwards. So you know that the work done for this case here should be negative. So, but since here that your y2 is greater than y1, if you're just going to directly use this term in the parentheses, it will give you a positive answer. And the negative sign here, it gives you the correction to your solution to the problem. Okay, for easy reference, you can just remember this one. Your work due to gravity is equal to mg y1 minus your mg y2. So this is more easier to remember. Now let's talk about the conservation of mechanical energy, or your conservation of energy. If you can remember, the conservation of energy states that energy can neither be created nor destroyed. So again, let me write it. Energy is neither created nor destroyed. So this is your conservation of energy. We're going to apply this one to the conservation of mechanical energy, which is just an extension of your conservation of energy. In the conservation of mechanical energy, the total mechanical energy of a system is the sum of its kinetic energy and the potential energy. So if you're going to use the symbol E for mechanical energy, okay, your mechanical energy now is just equal to the sum of your kinetic plus your potential energy. So a quantity that always has the same value is called a conserved quantity. Your mechanical energy is a conserved quantity. So if you start with some energy of 20 joules at later part, you should still have the same 20 joules of energy within your system. When the only force of gravity does work on a system, the total mechanical energy of that the system is conserved. This is an example of the conservation of mechanical energy. So the figure below illustrates the example. Let's say, for example, here you have a high jumper, and initially here, the high jumper is at at the ground, but if the high jumper moves, it has kinetic energy. So here, it has the kinetic energy, and if the only force acting on your system is the force due to gravity, when your high jumper jumps at this point here, let's say this is at point 1, and then at point 2, okay, you will, from your lessons in projectile motion, you'll see here that your velocity is equal to 0. So thus here, at this point here, your kinetic energy also is equal to 0. But the kinetic energy here at point 1 is not destroyed. It's just transformed into here a potential energy. Because at this point here, you now have some height h for your system. So from kinetic energy, your energy is transformed into potential energy. And as the jumper moves downwards in its trajectory, at this point here, your height is now equal to 0. Okay, but at this point here, you have your maximum velocity of your system. So back from your potential energy, it goes back again to into a kinetic energy. So your energy is transformed from kinetic to potential to kinetic again. In lesson 6, we have the work kinetic energy theorem that says that your total work is just equal to the change in your kinetic energy. So you have your work total is equal to K2 minus K1, or again you have your work is equal to your delta K. Again, that is your work energy theorem. Now, if gravity is the only force that acts, your total work is equal to the work done by gravity, and that is equal to the negative change in your potential energy, or you have your U grav 1 minus your U grav 2, 0.2, which we have discussed in the previous slide. And if we're going to put this one together, since these are just equal, these are just the same work that we are referring to here. If we are going to set these two apart, these two equations here, okay, and putting these two equations together, you have your delta K minus negative of delta U grav, or you have your K1 minus K2, that is equal to U grav 1 minus your U grav 2. And rearranging the terms, we put the initial points to the left and then the final points to the right. You have here your K1 plus U grav 1 is equal to your K2 plus your U grav 2. Again, your K plus your U grav is just equal to your total mechanical energy E. So that means here, your conservation of mechanical energy, you have here your E1, here this is your E1, and then this is your E2. So your E1 should equal to E2, meaning if you start with a mechanical energy of let's say 50 joules, you should end at the same total mechanical energy, 50 joules. So nothing should be, none of your energy should diminish. Okay. The conservation mechanical energy that tells us that your E is equal to your K plus U grav, and this one here should be constant. So on the next slide, I'm going to show you a video of what this actually means. So it's about a roller coaster. So let's see. So what we have here is it's not a roller coaster. It's a skateboarder. Okay, you have a skateboarder here, and what you will see here is this. You have this track for the skateboarder, and on the left side you have your kinetic, and you have your kinetic, and then your potential, and then some thermal, and then your total energy. So let's just disregard for the meantime this thermal part here, And let's just see what happens to your kinetic, your potential, and then your total energy. So when we say here, let me just write some things. So this is your kinetic energy here. This is your gravity, your potential energy due to gravity, and then here your total is your E. Okay, so let's see what happens to the video. So we have here, let's put it at some position here. And you will see here this total mechanical energy, your E. And as you can see here, your kinetic and then your potential energy graphs changes. But if you're going to sum these two, if you're going to sum the two graphs, it will always equal to this total energy here. So your green and then your blue bar graphs, when added together, will total to your this yellow-green bar graph here. So this is what we mean by your total energy that is conserved. So let's replay. So initially it has this total mechanical energy and potential energy at the top, but as you can see, while your skateboarder moves downwards, the potential energy decreases. Okay, so as you can see here, the potential energy increases when it moves upwards, meaning there's an increase in height, and as it moves downwards, the kinetic energy increases, because as it moves downward, the speed also increases. But again, the point here is that your total mechanical energy for your system should be conserved wherever you want to look at your system. So let's say at this point here, you have your E1 here, and you want to find the energies here, your E2. Your E1 should always equal to your E2. Okay, but of course there are changes in your potential and then your kinetic energy. So at here you have some initial height y1, and then here you have your height y2 at point 2. But at point 1, your velocity 1 is 0. But as you have seen, as it moves downwards, you have now some velocity b at point 2. So at here, at the highest point, your potential energy is at maximum, while your kinetic energy is 0 because it does not have any speed at point 1. If let's say you want to look at this point here at point 3, which is at the bottom, this time you have your y3, which is equal to 0, since this is just at the ground. At this point here, your potential energy is 0 because again your potential energy is equal to mg y, and your y here is 0, so that means at the bottom your potential energy is 0, and your kinetic energy is at maximum. Okay, so if here at this point, at point 1, we start with some potential energy, let's say you have 20 joules. At point 3, your kinetic energy is equal to 20 joules. So from your potential energy, it is fully converted into kinetic energy at point 3. Here at point 2, you have a mix of energies. So at point 2, you have some potential energy, and you also have some kinetic energy. Okay. Now, what happens if you have other forces that do work on your system other than the work due to gravity? Let's say, for example, in the previous video, we have your track for your skateboard, but we have assumed there that your track has a zero friction. But of course, in reality, your track should have some friction in it, because if there was none, the wheels in your skateboard will not roll, as you know. Now, if there are other forces that act on the body in addition to its weight, your total work now is equal to your work gravity plus some work other. And let's say that some work other is your friction. And if gravity is the only force that acts, you have your work other plus work gravity. Just like from the previous slides, we equate this one to your total work. We equate this one to your work energy theorem. So you have your work other plus your work gravity. This is equal to your K2 minus K1. And if we play with your equation further, you have your K1 plus K1 plus U grav 1 plus some work other. And this is equal to your K2 plus U grav 2. Here, when your work other is positive, if this is positive here, your energy increases. And when your work other is negative, your total mechanical energy decreases. Okay, so the effects of your work other is on your initial conditions. So it affects your initial conditions. Like say for example, in your track. So let's see an example when, or let's rethink the previous example. Now this time with your with some friction in your system. So what we have here is the same track, the same skateboarder, but this time we put here some friction in your track, and the friction is represented here as some thermal energy, because if you're going to try to rub your hands, you have there some friction, and as a result of this friction here, you release actually some heat into your surrounding. So you will feel that heat, or you will feel this thermal energy in your hands. So here your friction is represented as your thermal energy. So let's see what happens if we now have this friction in your track, and we have the same mass of your system, and we put your skateboarder at the same system or at the same position. So as you can see here, your kinetic and potential do not anymore reach the maximum total mechanical energy, unlike the previous example. What you see here is that as your time goes by, your thermal energy increases and your kinetic and potential energy decreases. So let's slow-mo it again. So you have maximum potential energy at the beginning, but as you can see, you cannot anymore reach the maximum potential energy. Some of the energy is transformed into the thermal energy. And as time goes by, your speed also decreases, so your kinetic energy do not anymore also reach the maximum kinetic energy. It also decreases, and your kinetic and potential energy slowly diminishes. But again here, the energy is not destroyed. It was just transformed into your thermal energy. We can use the same expression for the gravitational potential energy, whether the body's path is curved or straight. So, like say for example here on the first figure to the left. So here, this blue line here, blue dashed line is the path that your box takes from y1 to y2. But in talking about your gravitational potential energy, we're just actually interested with your points y1 and y2. So here, your gravitational potential energy, this is just equal to mgy1 minus your mgy2. So as you can see, we do not actually care about the path that it takes. So whether if your path here is a straight path from point 1 to point 2, the gravitational potential energy is still the same. And even if the path is like this, okay, as you can see, this path here is irrelevant when talking about the gravitational potential energy. We still have the same gravitational potential energy for your system. The work done by the gravitational force depends only on the vertical component of the displacement, delta y. It does not depend on the horizontal component of your displacement. We'll see in the next video if this is indeed true. If you try to remodel the track into something more fancier. So let's say, for example, you have this some kind of path for your system, but here your points 1 and points 2 are at the same height at y equals 6. So whatever the path it is going to take, whatever the potential energy here should be the same potential energy at this point here. Your energy should still be conserved. But of course, when you have some other forces, let's say that you have some friction, of course, you'll know that it cannot anymore reach point 2, and some of the energies will be transformed as heat, as you will see in the graphs. Okay, so the potential kinetic is slowly decreasing while your heat graph is increasing. So when your system finally stops, your initial potential energy is fully transformed into kinetic or into thermal energy at this point here at point 3. So here you have your maximum potential energy at 1. Your kinetic energy is 0. This is at maximum. So since at y2 you have the same height, you still have here the maximum potential energy, and your k is 0. At this point here at point 3, you have some your potential energy is, since we have here your friction, all your potential energy is transformed into thermal energy. So let's have an example. Your cousin Joe skateboards from rest down a curved frictionless ramp. If you treat Joe and his skateboard as a particle, he moves through a quarter circle with radius r is equal to 3 meters. Joe and his skateboard has a total mass of 25 kilograms. Again, your cousin Joe skateboards from rest down a frictionless or a curved frictionless ramp. So here you have some keywords: rest. If we treat Joe and his skateboard as a particle, he moves through a quarter circle with radius r equals 3 meters. So you have a quarter circle, the radius 3 meters. Joe and his skateboard has a total mass of 25 kilograms. Find his speed at the bottom of the ramp. So here, our target variable is your speed at the bottom, or let's say the speed at point 2. So this is here at your point 1, and then here is at your point 2. So the radius of the ramp, which is a quarter circle, is equal to 3 meters. So anywhere here you have your 3 meters, so that means the height from point 1 to point 2 is equal to 3 meters also. So this height here, this one here, okay? So let's solve the problem. So from your conservation of total mechanical energy, you have your E1 is equal to your E2. Okay, so we only have here gravity that does the work. So we have your kinetic energy 1 plus your U grav 1 This is equal to your K2 plus your U grav 2. But at point 1, as you can see at point 1, your kinetic energy is 0 because at this point here, your skateboarder is at rest. Your cousin Joe is at rest. So your kinetic energy at point 1 is equal to 0 because your velocity is 0 at point 1. And at point 2, you do not have any more some height because this is at y equals 0. So your potential energy 2 is 0. So let's just write the givens here for you to remember. So at point 1, you have your V1 is equal to 0, and then your Y1 is equal to 3 meters. At point 2, your Y2 is equal to 0, and then you have some velocity here that is what we are going to find. So again, your kinetic energy 1 at point 1 is 0, and then your gravitational potential energy 2 is 0. So we only have your U grav 1, which is equal to your K2. Okay, so this is equal to mg y1, and you have here 1/2 mv2 squared. So here, this is our target, your velocity 2. So you can play with your equation. So your velocity 2, this is equal to your 2 mg y1 divided by your m, and then you get the square root. So you have your v2 is equal to the square root of 2g y1, and you will get some answer for your velocity, which is equal to 7.67 meters per second. So you can verify it. And as you can see here, the weight of your or the total mass of your system is not actually involved in the calculation for the velocity. So here, your weight doesn't matter. But in later parts, you'll see that your weight put a special role, especially when you have your friction, because you know that your friction is equal to you have your mu n. So you have your normal force, so wherein your mass now takes effect. But for this case here, you see that in our calculation for the velocity 2, the mass of your system or the mass of your bodies are not involved in the masses are not involved in the calculation for the velocity in your system. So again, let's just summarize here. At point 1, you have everything at point 1 is just your U grav. Your kinetic energy here is equal to 0. And at point 2, your U grav is 0. And you just have some kinetic energy maximum. Now, suppose that the ramp is not frictionless and that the speed of Joe at the bottom is only 6 meters per second. What was the work done in him by the frictional forces? So here we have now your frictional forces that is involved in your system. So here our target now is the work other, or the work done by friction. So our target here is your work other or your work F. So just the same, from your conservation of energy, you have your E1 is equal to E2. We have K1 plus U grav 1, or let's just say U1 plus work other, and then this is equal to K2 plus U2. So our target is the work other, so your work other is equal to K2 plus U2 minus K1 minus U1. But here your U2 again is 0 because this is at the ground. Your K1 is 0 because you do not have your speed at the top of your ramp. So it's at rest in the beginning, at 0.1. So we just have your work other, and then this is equal to K2 minus your U1. So your K2 is equal to 1 half mv2 squared. So you have 1 half times the mass of Joule, and then times 6 meters per second squared. And you get your K2, which is equal to 450 joules. On the other hand, your U1 is equal to mg y1. Of course, your y1 is equal to 3 meters, and you have u1, which is equal to 735 joules. We use this one to find the work other. So you have 450 joules minus 735 joules, and you get a negative 285 joules. So your work other, or your work friction, is equal to negative 285 joules. So it decreases your the energy of your decreases the total energy in your system. That is your work friction is a resistive force. It is a non-conservative force. Sorry, it's your work friction decreases the your initial kinetic and then your initial potential energy of your system. But again, your energy is still conserved. It's just like your skateboard in the videos that I have shown you. So I'm going to leave you here with a challenge question. The figure shows two different frictionless ramps. The heights y1 and y2 are the same for both ramps. If a block of mass m is released from rest at the left-hand end of each ramp, which block arrives at the right-hand end with greater speed? So will the left ramp have a greater speed at this point here compared to this right ramp? So here, let's say this is your the speed here is v left, and then the speed here is vr. The question is, which block arrives at the right hand end with greater speed? Is it block 1 or block 2? So which do you think has a greater speed? Do you think that VL is greater than your VR, or your VR is greater than your VL, or do you think it is equal, or what do you think? So I'm going to leave this one to you to think about.